Okay, today we're going to discuss pressure in fluids and Pascal's principle. As a quick reminder, pressure is the amount of perpendicular force applied to a specific area. We can use this equation, pressure equals force over area. And we measure pressure in pascals, which is newtons per meter squared. And as a quick illustration of how pressure works, right? If we take your finger and apply some force onto your buddy's shoulder, you'll have a small amount of pressure. But if you take and apply that exact same amount of force with a needle or with a knife over a small area, then you'll exert a much larger pressure. And that's why some things are sharp, because they have a small area. So no matter what force you're using, you'll end up with a larger pressure if we use a smaller area. To demonstrate this idea of pressure, let's take a look at water under high pressure and what it can do to other materials or objects. So right here, we've got a lock. We'll see what high pressure water can do to that lock. So we've got a lock made of metal, which we typically consider a much stronger material than fluid water, than liquid water. And yet, under high pressure, water can be used to slice through a lock, slice through the metal that it is composed of. So that's the power of pressure. And if you wanted to take a look on our slideshow, there are 4 different videos here, the lock being one of them. But there's a few other videos of water being used to cut through much stronger materials when it is put under high pressure. And they're just kind of satisfying to watch. So go take a look at those in the PowerPoint if you're interested. All right, so next let's think about how pressure is affected by depth within a fluid. So, just to kind of tap into our prior knowledge here, can you think about the question, what is done to the cabin of an airplane as it ascends in altitude? So, as you go higher in the air in an airplane, what happens to the cabin? And if you've ever been in the cabin of an airplane, then you recognize that it has to be overpressurized, right? So your ears will pop, and the cabin ends up we end up pumping in additional pressure because as we go higher up in the air, the pressure in the atmosphere around the airplane decreases, which is why the airplane has to be pressurized to maintain what we're used to in pressure, even though the outside of the airplane is reducing in pressure as we ascend in height through our atmosphere. Something similar happens when you dive to the bottom of a swimming pool. What sensations do you end up with? And usually you can feel in your ears excess pressure beyond what you're normally used to. Because if we go down in a swimming pool to lower depths, then we end up with a greater pressure in the environment around us. So you'll see in the plane, we end up with a lower pressure as we go higher. And then in the pool, we end up with a greater pressure as we go lower. So clearly, there's a relationship between height or depth in a fluid and the pressure that's being exerted by that fluid. So let's explain and explore what that is. All right, so if we take a look at the fluid to the right, we have a fluid that is in a cylinder. So we have an area of this cylinder, and we have a height of this cylinder. And those two things will help us figure out what the volume of this water is inside, or whatever this fluid is, the volume of this fluid inside the cylinder. The matter constituting a fluid is going to have mass, and so it's going to provide force through its weight. So its force of gravity equals its weight equals mass times g, right? The acceleration due to gravity. So this means that the pressure and the force of a fluid is dependent on how much of the fluid is above you when you're inside of a fluid, or said a different way, rather than how much is above you, what depth you're at within that volume of fluid. So let's make an equation for this. Remember that pressure equals force divided by area. And again, our force from the fluid is coming from its force of gravity, right? So it is the mass times gravity of that fluid is what the force is, and then again divided by area. So we can take and let's figure out what how mass relates to the volume. So we know that our density of the fluid equals mass divided by volume. And so we can rework this equation to solve for mass. Mass equals rho, or the density, times V, the volume. And furthermore, we know that our volume for this cylinder is the area of the cylinder times the height of the cylinder. And so our volume equals A times H. And we can substitute that in for V. That gets us rho times A times H is equal to our mass, right? And then we can plug that in for mass in our top equation. So rho AH times G divided by A equals our pressure. And obviously we have two A's there that we can cancel out, and we end up with just rho GH left over. And that is our P, pressure. And this we call our gauge pressure. I'll tell you why in just 1 second, but just roll with it for now, okay? So our pressure equals rho GH. So if we know the height of our fluid that is above us, that times the density of the fluid times G gets us our pressure that the fluid is exerting on us. So let us run a quick example problem. So if this container were filled with mercury that has a specific gravity of 13.6 and it's filled to a height of 0.2 meters, how much pressure would the bottom of the glass feel from the mercury? And so we're going to, again, we will find our pressure is equal to rho times G times H. Now, if our specific gravity of mercury equals, remember, that equals our density of mercury divided by our density of H2O, right? So if we want to find our density of mercury, then we would take our specific gravity for mercury and multiply it times that rho H2O. And so we've got our specific gravity of mercury is 13.6. And remember that our density of H2O is 1,000 kilograms per meters cubed. And so our density of mercury is 13,600 kilograms per meters cubed. And we can plug that in over here. So our pressure is going to equal our density due to mercury, density of mercury. So 13,600 kilograms per meters cubed. Then we'll times G, which is 9.81 meters per second squared. And then we'll multiply it by our height, which the height of the fluid is 0.2 meters. We plug that into the calculator, we end up with 26,700 pascals is the unit that we measure pressure in. Or if we wanted to communicate that in kilopascals, it'd be 26.7 kilopascals. All right, so now that we know our pressure from that height of mercury, let's think about if instead of our mercury being in this glass, we ended up with a vat of mercury that had the exact same height, but had a much larger area. Let's say 100 times the area of our original glass here, but it's still the same height. And so hopefully, as you can tell from our equation right here, since the area and the overall volume of the liquid doesn't show up in our equation, all that matters is our height. Actually, we would end up, if this were the case, if we placed enough mercury in a vat with 100 times the bottom surface area, but the same height/depth, we would end up with the exact same amount of pressure. There wouldn't be any change in our pressure, no matter how large we expanded our vat, as long as the height stayed the same. However, we haven't yet shown the complete picture because outside the fluid, there's going to be the environment, and the environment's going to have some pressure as well. And this external pressure is going to be pushing down out of the fluid, and it can be contributing force in addition to the weight of the fluid. And so when we think about the pressure of the fluid, it's going to be pushed down by that external pressure, and that external pressure is going to be added to the pressure of the fluid that we already found. So let's think about atmospheric pressure real quick, because generally the outside, the external environment is going to be the atmosphere under most circumstances. So the atmospheric pressure is the pressure exerted by the Earth's atmosphere on average at the Earth's surface. This will obviously vary with altitude and with temperature and with local weather systems, but we can kind of assume that it's generally what we call 1 ATM's worth of pressure, or 1 atmosphere. And again, that's the average pressure on Earth's surface. And this equals about 1.013 times 10 to the fifth pascals. So 101,300 pascals. Another way to express this is with bars, and 1 bar is 1 times 10 to the fifth pascals, so 100,000 pascals. And so 1 ATM is just 1.013 bar. And this unit of bar is typically used in meteorology when discussing weather systems. And another common one is millibars. And so 1,000 millibars is equal to 1 bar. So 1.013 bars is 1,013 millibars. And this is all equal to, if you wanted to put it into imperial system, into our imperial units, it's 14.7 pounds per square inch. So if a system is exposed to the environment, then we can generally assume that the external pressure of the system is PATM, or 1 ATM's worth of pressure. So unless we know otherwise, then we can assume that's the case. All right. Okay, so let's think about atmospheric pressure in terms of a problem. So, atmospheric pressure originates from the amount of air that is above you, which has a low density, but there is a lot of it. And just as a point of information, the troposphere, which is the section of the atmosphere that we live in, it's the lowest and densest portion of the atmosphere. It extends to around 8,600 meters above us. So let's figure out what the density of air is. Remember, it should be about 1.2 kilograms per meters cubed, but let's try to find it. So we know that pressure equals density times G times H. And so if we want to find our density, that's going to equal our pressure divided by G times H, right? So, and our pressure of the atmosphere is 1 ATM. So that should be 1.01 times 10.013 times 10 to the fifth pascals. And we'll divide that by 9.81 meters per second squared. And the height of our atmosphere is about 8,600 meters. So if we take 1.013 times 10 to the fifth, divide by 9.81, and divide by 8,600 meters, we get 1.20-ish kilograms per meters cubed, which is the density of air, the approximate general density, average density of air. So great, everything's working as it should be. All right, so let's now try to figure out what mass of air is above your head. So if you're standing in the atmosphere, as you currently are, above your head, there's going to be a column of air, right? And we don't usually think of it like this, but that air, all those particles do have some mass to them, right? And so they have some weight to them. And that pressure is being applied to your head. So if your head has a radius of 0.087 meters, that's going to give us an area of pi r squared. So pi times 0.087 meters squared. That's going to give us an area of 0.0238 meters squared. And so that's the area of this column of air. And the height is 8,600. So if we want to think about the volume of that column of air, that's going to be the area times the height. And so that volume of the column of air above your head will be 0.0238 meters squared times 8,600 meters. And that would get us 204.5 meters cubed. So the volume of air above your head is about 204.5 meters cubed. And lastly, we know that our density for any substance is its mass divided by volume. So if we want to find our mass, we will take our density times volume. And since we already found our density of air was 1.20 kilograms per meters cubed. So we'll take 1.20 kilograms per meters cubed, multiply that times our volume, which is 204.5 meters cubed. The meters cubed cancel out, and we end up with some number of kilograms of air above our head, and it'll be about 240-ish kilograms of air above your head. So that is a lot of air above your head. And we don't usually think about it. And the human body, just like any animals on the surface of the earth, is adapted to that amount of force, right, of gravity from that amount of that volume and mass of air above our heads. So this essentially is what 1 ATM's worth of pressure is. It's all that air above us pressing in on us at all times. And that's why when we think back to the airplane, why we had to pressurize a cabin is to maintain that external pressure that our body, the human body, is used to. All right, so let's go back to our gauge pressure. So remember that our gauge pressure is equal to rho GH, right? The density of the fluid times the gravity times the height of that fluid above us. However, again, we have that external pressure, that outside pressure on top of our gauge pressure. So we need to combine those two things to get our full measure of pressure acting on an object within that fluid. This is called the gauge pressure because most pressure gauges are calibrated to treat the external pressure, usually, again, atmospheric pressure of 1 ATM's worth of pressure, as zero. And so, for instance, when you think about like measuring the tire within your car, if you take a little tire gauge, then that gauge, usually our tires for a car want to be at about 32 pounds per square inch to use the imperial system. But if that gauge were to read zero, if we read zero on that gauge over here, that just means that inside the pressure is 1 ATM's worth of pressure, meaning the pressure inside, P in, equals the pressure outside, right? Or P naught. So when those two equal each other, that's when our gauge pressure is zero. So our gauge pressure really tells us how much additional pressure do we have within the volume that we're measuring the pressure of relative to the external or environmental pressure. And if we wanted to get a full measure of the total pressure inside of a volume, we want to take the absolute pressure. So the absolute pressure of a fluid is the total pressure at a certain position within a fluid, both the pressure from that fluid itself, which we call P gauge, and the external environmental pressure, which we could call P naught, that external pressure. And usually that P naught is going to be PATM, or 1 ATM's worth of pressure, 1.013 times 10 to the fifth pascals. And we can set that up with this equation. So our absolute pressure, or P, naked P with no little zero or anything next to it, is going to equal P naught, the external pressure, plus that gauge pressure, rho GH, the volume of the fluid of interest above us, times G times its density. So if the container again was now filled to a height of 0.2 meters with glycerin, which has a specific gravity of 1.26, what should the gauge pressure be, and what would the absolute pressure be? And I'm not going to go through finding the gauge pressure right now, because again, all we need to do is use that density of glycerin times G times H, which we did in a few slides ago with mercury. But just to take a look at how this would change in terms of our absolute pressure equals P naught plus our gauge pressure. And since our P naught is 1.013 times 10 to the fifth pascals, since that's probably an atmosphere's worth of pressure, we're going to add that to the 2.47 kilopascals, so 2.47 times 10 to the third pascals. And if we add those together, we end up with 1.0377 times 10 to the fifth pascals, or 104 kilopascals. So that's how, if we know our gauge pressure, we can add it to the atmospheric or the external pressure to get our absolute pressure. So on the bottom of this glass right here, if this were made of glycerin, right, and if it was at a height of 0.2 meters, and the external pressure were PATM, we're just an atmosphere's worth of pressure, then our absolute pressure would be 1.04 times 10 to the fifth pascals, because our pressure, our absolute pressure, will equal our P naught plus our P gauge. And that means that our P gauge, our gauge pressure, is actually just our absolute pressure minus our external pressure. All right, so take what we just learned about depth and height of the fluid above a point and how that relates to pressure, and try to figure out what that has to do with the shape of dams. So the Hoover Dam is pictured to the left, and you'll notice from that picture that it has a structure that is similar to the diagram to the right. So take a minute and think about why there is this enlarging structure as we get deeper and deeper along the dam, why our base needs to become wider and wider as we go. And do the same thing with a swimmer in the water. So the reason that a fluid exerts pressure, right, is because it will fill in all of its available volume unless it's obstructed. And a swimmer is an obstruction to the water. And so obviously this water is going to exert pressure on the swimmer. Why is it the case that the force arrows on the top of the swimmer are smaller, indicating a smaller force, than the force arrows on the bottom of the swimmer? Think about why that is. All right, so when we apply pressure to a fluid, that's not so easy to do. So if you ever tried to push on water with your hand, obviously the water just flows around your hand, right? But if we enclose the fluid, then it becomes easier to apply pressure to that fluid. And that pressure is going to be transmitted throughout the whole fluid undiminished. That's what our boy Pascal, that's what Pedro Pascal, that's what Blaise Pascal, for whom Pascal's principle that we'll discuss in a moment was named after. That's what he determined, is that the pressure of fluid is transmitted throughout that fluid undiminished. So Pascal's principle / law states that the pressure applied to an enclosed fluid is transmitted undiminished to every portion of that fluid and the walls of its container. So what this looks like is, let's say that we have some fluid contained within these two vats that are connected by a channel in between them, all right? So if we have some sort of a piston or something that will press in on the fluid, when we push down on it, we're going to apply some pressure onto that fluid. And that pressure is going to be exerted along every portion of the fluid. So every wall of the container will feel that pressure. And as we increase that pressure, then that pressure is going to increase on every wall of the container. By Newton's third law, any force applied to the fluid will cause an equal and opposite force from the fluid, and that's the pressure we're going to feel exerted on the walls of the fluid of the container. So if we look at the scenario on the right, we have some force 1 pushing down on this small vat right here, which has a pump right here, a piston that has some area to it, right? So this is going to have some area. This is going to be a cylinder, and that cylinder is pushing down on the water. And we're pushing down with some force F1. And that force, since pressure equals force divided by area, then that force is going to equal the pressure at point 1 times the area at that first piston, right? Since we know that pressure equals force divided by area. And we know the same thing can be happening over at point 2 over here. So again, this piston is going to have some area to it, right? It's going to have some area, and it's going to feel some pressure coming up from the fluid. So that force, that pressure at point 2, it will equal the force at point 2 divided by area of that second piston. So pressure is applied equal to every portion of the fluid and all contact surfaces, which means that P1 will equal P2. And furthermore, we can set up an equation that relates to force felt at each position divided by the area of each piston. And this really is Pascal's principle boiled down to an equation, which says that the force at point one divided by the area at that point will equal the force at a second point divided by the area of that point. And this principle of Pascal's will give us something we call mechanical advantage, because you'll notice that that F2 will be significantly larger than F1, right? Right here, this force coming from the larger area piston will be significantly larger than the smaller force we exert onto piston one. And so, us humans, we use this in our mechanisms and our machines in order to gain a mechanical advantage, meaning use a small force and multiply it to become a bigger force when we set up a system like this. And so this is due to the force multiplying effects of what we call a hydraulic system, is what we've got here when we have two piston pumps of varying sizes. And so we can put a small force on one and observe a larger force coming from the other one. So we end up with force 2 equals the quotient of those two areas times force 1, right? So if our area 2 is larger over here, then we're going to end up with a larger force coming from coming at that from that piston. So when A2 is larger than A1, then F2 will be larger than F1 by the same factor. And this is what we call mechanical advantage. So let's put Mr. Pascal's ideas to use using something that we should be pretty familiar with, a car's braking mechanism. Let's figure out how it works. All right, so the first aspect of a car's braking mechanism is we're going to take a pedal, the pedal with your foot, and we're going to press into that. And that pressing into that, our pedal is a lever. And so we know that whatever we press into it, we'll end up with a torque. In this case, this is a counterclockwise torque, and that will push the pedal into this pedal cylinder over here, compress this, and whatever it compresses it into, this is going to push back out with a force as well. And this will be equal to this force 1 that we're pressing in with. So the pedal will push in with some force that the pedal cylinder will push back out with. And that will create a torque, and that's a clockwise torque. And so obviously, since our net torque is going to equal 0 here, then our torque in the counterclockwise direction has to equal our torque in the clockwise direction. So I'm going to leave that up to you to figure out how this force F1 right here relates to, or calculate how it relates to the force that you're pushing with the pedal. But ultimately, we should end up finding that our force F1 right here is 500 newtons, or 5 times the force that we're pushing in with our foot on the pedal down there. All right, so now what's cool is that now we know how a brake system essentially works, right? So we applied some force into the pedal here. We're going to call that F1. And that pedal pushed into this pedal cylinder that has some area, right? And that increases the pressure of this fluid, and the fluid is connected to wheel wells within the wheel cylinders of your car. And then that exerts a new pressure, F2, relative to that pressure of the fluid, sorry, a new force, F2, relative to the pressure of that fluid, that then pushes out onto the brakes and then causes your car to stop by applying that force onto the brake pads and exerting that onto the tires to slow them down. All right, so this, we can figure out just how much force, because we know our force we applied up here at the pedal, and we know the area of the pedal cylinder and the areas of the wheel cylinders. So let's take, and considering we know that if this is point 1 up here, right, so our pressure at point 1 is going to equal the pressure within the fluid at point 2. And we know furthermore that we can relate pressure to force and area. So our force at point 1 up at the pedal divided by the area at the pedal is going to equal the force at the wheel cylinders divided by the area of the wheel cylinders themselves. Or if we want to find the force over here that's being exerted on the brakes, that's going to equal A2 over A1 times F1. And now for any of our areas, right, if we know the diameter, we can find our area is going to equal pi times any diameter divided by 2 squared, right? Or pi r squared. So we can take and we can translate this into pi times d2. So our area equals pi times d2 over 2 squared divided by pi times d1 over 2 squared, or the area of 2 divided by the area of 1. And then still times f1, right? And some of these things are going to cancel out, right? The pi's are going to cancel out. And the 2 squared in the denominator of both the numerator and the denominator are going to cancel out. And so we will end up with simply d2 squared divided by d1 squared times f1. That will equal the force exerted on the wheels, on the brakes by the wheel cylinders, right? So you take those numbers, and D2 is 2.5 centimeters. I can leave these in centimeters if I wanted to, because the centimeter squared on the top is going to cancel out with the centimeter square on the bottom. So we don't need to convert those into meters if we don't want to. And then, so that's our diameter 1 at the wheels, diameter 2 at the wheel cylinder squared, 2.5 centimeters squared divided by 0.5 centimeters squared. And then times our force 1, which is 500 newtons. If we take 2.5 squared divided by 0.5 squared and multiply that times 500, then we should end up with 12,500 newtons. Or, if we want to put that into simpler units, 12.5 kilonewtons. So, what do we see? We see that if we take and apply pressure onto a brake, we have this little lever system, right, created by the brake itself that will apply some pressure onto that pedal cylinder. And then that pedal cylinder will communicate that pressure through the brake fluid to the brakes themselves. And since we use Pascal's principle there, we'll get this multiplying effect that 500 newtons that was applied at the pedal cylinder becomes 12.5 kilonewtons. Becomes a lot more kilonewtons, or a lot more, a much larger force than what we applied here. And what we applied, because we had a lever up here, was even smaller, right? It was only 100 newtons. So from 100 newtons, we get a significant force over at our brakes. So that's how a hydraulic system of your brakes in a car will work. Isn't that fun? So this is combining a bunch of simple machines. We've got a lever here at the brake, at the brake, the brake pedal, and then we have a hydraulic system here that connects the brake pedal to the wheel cylinders. So neat. All right, and then what happens when we add wheel cylinders? And basically, we already did this, right? So in our diagram over here, we showed the pedal cylinder and then fluid going to 2 wheels. We only dealt with 1 wheel, right? So you'd probably imagine that adding a second wheel actually is going to change anything. And that is the case because as long as we have additional brake fluid to fill up this wheel well as well, as long as we fill up this entire line and each wheel well, then remember that Pascal's principle is that the pressure exerted by a fluid will be communicated undiminished through the entire volume of that fluid. So it doesn't matter how many output pistons we have, as long as we fill them up fill up their entire volume with fluid, then we can exert that same force at each wheel cylinder that is proportional to the area of that cylinder relative to the area at the pedal cylinder where we applied our original force at the pedal. And finally, we can think about our mechanical advantage here. So again, mechanical advantage is the amount an input force is multiplied to produce the output force for a simple machine, such as a lever, like our pedal, or a hydraulic system, like our whole brake system over here. So our mechanical advantage equals F output over F input. And let's think for a moment about the mechanical advantage of the lever system and the brake system. So remember that F1 up here, we ended up with 500 newtons worth of force when we applied 100 newtons worth of force down at a lower lever arm length or a longer lever arm length at the end of this pedal, right? So for our mechanical advantage of the pedal, which is a lever system, will be our force, our output force, which is F1 right here, divided by our input force, which I'll just call F foot, which equals 500 newtons divided by 100 newtons. All right, so 500 up here and then 100 down here. And so that equals 5. So our mechanical advantage for the pedal system right here was 5, which just means that whatever force we applied here, we had 5 times the force being applied onto the pedal cylinder up at the higher end of this lever, this pedal that acts as a lever. And then we can also find our mechanical advantage for the brakes. So MA brakes equals F1, or sorry, F2, our output. So our output is F2 over here, which remember that was 12,500 newtons. So F2, and then divide that by our input force, which was F1 up here. So F2 over F1, and that again is 12,500 newtons divided by 500 newtons. And if we divide those out, we end up with a multiplication of 25x the amount of force. So whatever force we apply up here, we get 25x that amount at the brakes and at the wheel cylinder. So if we put 100 newtons worth of force up here, we'd end up with 2,500 newtons worth of force down there. All right, one last little thing. Delta P. Say for delta P, right? Change in pressure. Change in pressure. So if we have two different volumes of fluid and there are different pressures, when they meet, they will seek to equilibrate, causing a flow of fluid between the two of them. The larger the difference in pressure, the larger the force exerted by the flow between the two volumes. And let's take a look at a quick video that illustrates the danger and the power of delta P, of two different pressures when that difference is significant. All right, so we're going to take a look at this video, which is linked in the slide, and we're going to have a saw that's going to drill into a pipe. Inside the pipe is very little pressure. Outside the pipe is a lot of water, so a lot of pressure. And we'll have a little crab that's walking by, and you'll see that there's a difference in pressure inside the pipe and outside the pipe. And the difference in pressure is so significant that the crab, the poor little crab, actually gets crushed and sucked in. And this is the power of a difference in pressure between two different volumes of liquid. And this is just another example of the power of pressure. All right, so that closes things off for today. In class, we're going to take a closer look at pressure, work on some problems, and attempt some different scenarios. All right, thanks for learning today, guys.